Hi everyone, welcome back to Botronix Lab's Robotics course for beginners. In this Module 7, we'll be learning how to control a 4DOF robot arm using MicroPython on the Raspberry Pi Pico. This module is part of our fundamental course series, and today we're focusing on smooth servo movements to make your robot arm behave more naturally, like a real robotic manipulator. The 3D printed robot arm design we're using is called Pedro 1.0, created by almtzr. This design is available under the Creative Commons Attribution license, so big thanks to almtzr for sharing this awesome open source project. In this module, we'll be working with a 4 degree of freedom, 4DOF, robot arm, fully assembled using 3D printed parts from the Pedro 1.0 project by almtzr. On your screen now, you'll see two important diagrams. First, the mechanical assembly diagram, which shows how each servo and 3D printed component fits together. Next, the circuit wiring diagram, where you can see how the 4 servo motors are connected to the Raspberry Pi Pico. Base rotation is wired to GPIO2, shoulder joint to GPIO3, elbow joint to GPIO4, gripper to GPIO5. Each servo is powered through a separate 5V power supply to ensure stable current delivery, and all GNDs are tied together to form a common ground. If this is your first time assembling a robot arm, don't worry. While this module gives a quick overview, I'll also prepare a dedicated assembly tutorial video that goes through each part and wiring connection step by step. So feel free to follow along visually for now, and stay tuned for the detailed build guide if you need extra help. Let's move on to understanding how the servos function. Before we dive into the code, let's take a moment to understand something important in robotics: degrees of freedom, or DOF. A degree of freedom simply refers to how many independent ways a robot joint or part can move. For robot arms, each servo motor typically provides 1 degree of freedom. It can rotate to position a joint in a specific angle. In our case, the robot arm has 4 degrees of freedom. Base rotation allows the entire arm to rotate left and right. Shoulder joint lifts the upper arm up and down. Elbow joint bends the lower arm forward or backward. Gripper opens and closes to grab or release objects. Each of these movements is powered by 1 servo motor, and they combine to allow the robot arm to reach and interact with objects in a 2D or 3D space. If you've seen industrial robotic arms or advanced robotic kits, you may have heard about 6DOF or even 7DOF robot arms. These have extra joints, like wrist rotation or tilt, more flexible elbows, rotating grippers. These allow for much more complex and precise movements, similar to a human arm, and they're what we'll cover in advanced-level robotic courses in the future. But for now, mastering 4DOF will give you a solid foundation to control real-world robots using MicroPython and electronics. Alright, let's now move on to testing our robot arm. In this part of the module, we'll run some simple MicroPython code to move each of the 4 servos, base, shoulder, elbow, and gripper, individually. This will help us verify that our wiring is correct and that the arm is properly assembled. Here's the code we're using to test the servos. In the script, we first center all servos to 90 degrees, which is a good neutral position for most robot arms. Then we move the shoulder servo to 30 degrees to simulate lifting the arm. Finally, we open and close the gripper by moving it between 0 and 180 degrees. This testing routine is essential to ensure your servos are working correctly and that the robot arm joints are not obstructed. Learning point: servos are controlled by sending them specific pulse widths, which we convert from angles using a helper function. This abstraction will make it easier to build complex movements later. Once this is working correctly, you're ready for the next step: creating smooth sweeping movements and action sequences. Let's go! Now that we've confirmed each joint of our robot arm works correctly, let's make the movement smoother and more lifelike. In this section, we'll introduce a new feature called sweeping motion, which gradually moves the servo from its current angle to a target angle step by step, similar to how a real robotic arm would move. We'll use this code to do it. Rather than jumping straight to an angle, this approach slowly transitions between angles, making the motion look natural and realistic, ideal for robot arms that need to handle or demonstrate smooth actions. You can also adjust the step and delay values to control the speed and smoothness of the sweep. This completes our first simple action sequence: pick, lift, drop, and rest, all with a natural-looking animation. Congratulations! You've just completed Module 7, where we explored how to bring our 4DOF robot arm to life. You learned how to connect and control 4 servos using PWM, test individual servo angles manually, and implement smooth sweeping motion for more realistic robotic behavior. This module is a big step forward in our Pico robot arm journey. You're no longer just assembling hardware, you're now making it move with intention and precision. In the next module, we'll go further by using joystick input to control the robot arm interactively, like a real robotic manipulator. If you have any questions or want to share your robot's progress, feel free to leave a comment or tag us. We'd love to see your robot arms in action. Don't forget to like, subscribe, and stay tuned for the next module. See you next time at Botronix Labs.